Me and Ava have decided to research and present on the A-star algorithm. So the goal of the A-star algorithm is to find the shortest path between two nodes. So if you're starting at node S, the algorithm says to look at all of its neighbors, so A, B, and C, and compare each of their weights. So A has the smallest weight, which is 4. So next we're going to jump to node A. Now we have to compare all of the new paths. So we have to compare S to A to D, S to A to B, S to B, and S to C. And when we compare all of those paths, S to A to D has the shortest weight of 9. Then you rinse and repeat until you eventually have made it to the goal node. This is some bare bones pseudocode that I wrote. So it's basically saying the same thing as before, where you have a starting node and a goal node, and we also have to keep track of what the current node we're on is. And we're going to keep, this while loop says to keep traversing the tree until we've reached the goal node. And every time we traverse, we're going to make a new list of all of the neighboring nodes of the explored nodes. And then we're going to compare all of the neighboring nodes, all of their weights, and whichever one has the lowest weight is where we're going to jump to next. So what I've explained so far is also how Dijkstra's algorithm works, but how they differ is right here. It's how you calculate the weight. So if f of n is the total weight of a node, Dijkstra's algorithm only takes into account g of n, which is the cost from the start to that current node. But the A-star algorithm also takes into account h of n, which is a heuristic function. And this heuristic function is, it will change depending on what you're trying to do. And you as the programmer have to decide how you write it. And this will make more sense on the next slide. So on a problem like this, where you're trying to solve a maze, you can write a heuristic function that encourages the algorithm to explore nodes closer to the finish line. So, and so if you're starting out the red square and you're trying to get to the green square, um, Dijkstra's algorithm is going to struggle on something like this because each square on the maze has the same exact weight. So it has no idea how to find the fastest path, and it has to explore a lot, almost everything until it just stumbles into the finish line. Whereas the A-star algorithm, we can add a heuristic function which will encourage it to explore the nodes that are closer to the finish line, and it will get there a lot faster. This is some code that we wrote to compare the two algorithms, and the next slide will present the data in a much nicer format.
Now I'll compare A-star to Dijkstra's algorithm. On the left is the unsolved maze. The green square is the start, and the red square is the end. In the next picture, you can see that Dijkstra's algorithm had to visit all but one of the squares to find the shortest path. A-star had to visit 3 fewer squares to find the same shortest path. This may not seem like much of a difference in such a small maze, but if you expand this to larger maps, the difference is significant. The time complexity for A-star is defined by B, the branching factor, which is the average number of child nodes, and D, the depth of the shallowest solution. The worst case occurs when every possible node is fully expanded, and the best case occurs when only the necessary nodes are expanded during the search.
The creators of the A-star algorithm were working on a robot that they wanted to plan their own movement. So Nils, he first proposed writing an algorithm that estimates distances to the goal, which is the heuristic function. Bertram suggested adding the cost from the start, which is kind of like Dijkstra's algorithm, and then Peter helped introduce key concepts and refining their algorithm, and so together they came up with the A-star algorithm.
A-star is a pathfinding algorithm. This means that it can be used in any setting where you need to find a shortest path. I will discuss it more in the next section, but because of A-star's heuristic weight adjustment, it is more efficient than Dijkstra's algorithm. This algorithm is a top choice in map navigation. A-star is much faster than Dijkstra's algorithm and has to search fewer nodes to find the shortest path. A-star is also used in autonomous vehicle pathing. This includes driverless cars, Roombas, and the next example, Micromouse. Micromouse is a competition that combines the fields of engineering and computer science where teams compete to build a palm-sized robot that can navigate a maze the fastest. A-star is one of the many algorithms chosen for its efficient use of time. These are the sources that we used for our research.